lesson 2 in the second unit, and it's on scatterplots and correlation. So these are the AP Classroom videos, and I would tell you that these are probably not very important for you to go watch. We've done scatterplots before in your other math classes, so unless you have a question over what we do today with correlation, these are videos that would just be support. They're not required. Okay, so here we go. Says when we want to evaluate the relationship between two quantitative variables. So remember, when we have two variables, we also say that this is bivariate data. I don't know how to spell that. Bivariate data. And so this just meaning we have two variables that we're looking at. So when we look at this graphically with quantitative data, we are going to start this with a scatter plot. And here's a scatter plot. You see this in your notes here. And so the scatter plot is just a series of dots. And so it says that it shows the relationship between two quantitative variables. So here we have arm span on the x-axis and we have height on the y-axis. And so what they're saying is the arm span of, let's just say, basketball player, arm span of a basketball player is correlated to the height. All right. So when we do this, we have to identify the variables that we have. So we've talked about exploratory and response variables, but a variable that measures the outcome of the study, so it measures the outcome, that's going to be the response variable. And our response variable is usually what's on the y-axis. So remember, think about this. F of x, we plug this in and we get a result, and the result is the y value. And then what we have on the x-axis is the explanatory variable. And that's normally our x. And it's the variable that helps explain, explanatory, or influence the change in the response. So this would be the x in an f of x function. Okay? So we see these often as dependent and independent. I think we've talked about this before, but our x variable is explanatory. And it is also considered our independent variable. And our y variable is the response. And that's going to be dependent. It's dependent on whatever our x value is. Dependent. Okay. So when we look at a scatter plot, there's a few things that we're going to look at here. So in the graph, so once we have this plot, right, we want to look for an overall pattern. All right, so it's the same thing when we were looking at distributions. So when we looked at a distribution, whether it was a histogram or a bar chart or anything, we're looking at this overall pattern and we're seeing, do we have something that is an outlier? Do we have something that can define this? And that's all we're doing. So we're going to do the same thing. We're going to describe the overall pattern of a scatter plot. So if you remember when we were describing these relationships, we used this acronym SOX, right? So we had shape, outliers, centers, and spread, or variability. Well, when we're describing a scatter plot, we're still going to talk about some of these things, but we're going to use a different acronym. So the first thing that we're going to talk about is direction. So with this scatter plot, this is going up, so I would have a positive direction. We're going to talk about the form. Because this scatter plot is a line, then my form would be linear. We're going to talk a little bit about the strength of the scatter plot. The strength. And the strength is basically saying how close are all of these data points to fitting on this line. So this is pretty strong. If you look, maybe we've got one little outlier here, but for the most part, we have a pretty strong correlation. So that would be the strength. And then an important kind of deviation. So the deviation that we would have, I'm going to call it an outlier right now, but what you're going to find is that these are really going to be leverage points. We're going to get into more detail on outliers on a scatter plot. But what we're looking for is just something that deviates from this plan, right? So this one is a little high up, so we could say that that might be an outlier. Okay? All right, so this talks about this acronym that we're going to use when we define or describe a scatter plot, and we're going to use DUFs as our acronym. So direction, unusual features, so same thing that we had when we had our outliers. So we're looking for outliers, we're looking for gaps, we're looking for clusters. And I'm going to go ahead and put this up here again, leverage point, because you're going to see that come back when we get into more detail. The form, is it linear? Is it non-linear? In fact, it's okay to just say non-linear. If you don't know exactly what type of form it is, we know that it's not a line. The strength, so how close to the points lie. The association, can one variable predict the other? So we're going to talk a little bit more about association. And then always context. Always context. Okay, so what do these look like? If I have something that's positive, that just means that the overall slope of the line is going to look positive. If I drew a line through this, it would be up, and it looks, all my values are going up. If I had something that was negative, obviously it's going to be something that looks like this, where I could draw a line through this, and I'm going to have a negative line. Now, this is important, and this would say no association. Even though we're going to talk about correlation, we use the word association, don't use the word correlation. And that just means that you're going to have data that's kind of all over the place. And so I can't draw a line that goes down. I can't draw a line that goes up. It's just, there's no association. It's not linear. There's no pattern to the data. In fact, let me put this here. There's no pattern. Okay, so what does this look like with my unique features? So my unique features, I could have outliers or influential points. And so what would happen if I have this data, and let's just say that I've got this data that looks like this, and then I have a point that's up here, and I have a point that's over here. This point, if I drew my line through this data, this point up here would be a definite outlier. And I would say this because it is far from this graph. So far from my best fit line, so this point would be an outlier. This point, however, would be an influential point. We would probably call this a leverage point, but I don't know exactly, so I'm just going to say it's an influential point. That means that it follows the general path of this line. If I drew my slope even a little bit higher, which I probably should have right here, if I have something, it falls away from this data. So if you look on this x-axis, this data is farther apart, but it kind of is not completely off the line, okay? We might have gaps, just like we would have in a histogram. So we would have some data that's here, and then all of a sudden we have data that's up here. So that could be something that would be a gap. So we see this gap that's right here where there's no data. And then we could also have clusters. And we see this more often on a scatter plot where we have something that maybe looks like this. And this would tell me that I would have a cluster here and maybe another cluster up here. And it's okay to have more than one cluster, all right? So a cluster would just be the same thing that you would see on a histogram or a dot plot. It's just a bunch of data clustered together, okay? So if we have a linear graph, it's going to look like a line. It doesn't matter if it goes up or down, and it does not have to be perfect, but we have something here where we can see that if I was to draw a line through this pattern, it's going to look like a line. I might have something that's exponential, and remember with an exponential function, you can have growth or you can have decay. You can have one that goes up or you can have one that goes down. So I might have something that looks like this, definitely not linear, and then it's starting to curve off maybe this way. And this would be something that would be an exponential decay graph, right? Definitely not linear. I could have growth, it would just be going in the other direction. Right? And then another option of something that we might see would be something that would be a little bit logarithmic, and it could look like this. Now, if you look at this graph, and this is the one that I think is the most tricky, I could draw a line through this data right here, and I could make this linear. If I drew an exponential curve through this, and it looked like that, I might fit more data. And so we don't really know. In fact, I'm going to just draw a dashed line through here. so that you can see how this dashed line could make this look linear. Is it linear or is it logarithmic? So we're going to look at how we determine this through this correlation constant that we're going to have here in a minute. But that's why sometimes when you're doing your descriptions, it's better to say nonlinear, because we don't want to call something out if it's not really that shape. Okay, and then let's talk about strength. So if we have something that's weak, that means that we're going to have points that are going to give us some sort of pattern where I would have a linear function, but I don't really hit very many data points, right? I can see that my line goes up, so this would be positive, but it's pretty weak. If I had something that was more moderate, then my data points are going to be a little bit closer together. So something that looks more like this. So when I draw my best fit line here, I'm much closer to all of my points than I was on this one. And then in fact, the way I drew this, I'd probably say that this is a strong correlation, because it's very rare that you're going to get a correlation that looks like this. And that would be a perfect correlation, which would be very strong. I hit all my points, so this would be a strong correlation. In fact, I would even say very strong on this one. But like I said, the way I drew this would probably actually be moderate. Or sorry, probably be strong. And so this is subject to interpretation. When you get numbers, it's going to be more obvious. Okay? All right, so let's talk about how we create this scatter plot on a calculator. You might remember how to do this from your previous classes. Go ahead and make sure you have your calculator so you can walk through this with me. So it says, suppose we hypothesize that the number of doctor visits a person can be explained by the amount of cigarettes they smoke. We want to see if there's a relationship between the number of cigarettes one smokes in a week and the number of times per year they visit the doctor. So they randomly selected 10 people. So here's what we're going to do. The first thing that we need to do in our calculator is make sure we don't already have something set in y equals. So I'm going to clear that out. I need to put my data in. So to put the data in, you're going to go to Stat. I have this written here. You're going to go to Stat, and then you're going to go to Edit. And I'm just going to put this data in List 1 and List 2. So List 1 are going to be the cigarettes, because that's my explanatory variable. How many cigarettes do they smoke? So 0, 3, 21. Okay. And then I want to see what the response of that is, and that's the number of doctor visits. So 1, 2. Okay. Now, super important, just look at it briefly, make sure you don't have some crazy outlier where you mistyped or put a 0 in, and then you have to make sure that your list 1 and your list 2 values are the same. All right? So next we need to make sure that our stat plot is even on so that we can graph this. So to turn your stat plot on, it's right here, stat plot. So it's going to be second y equals. Right now mine's off, so I hit enter. I'm going to go here to on, turn it on. The first type that you see is the little stat plot button. You see all the little points. Now I'm going to tell it where to pull the data. So obviously I was doing something different on my calculator. Let's see if I can make this a little clearer. There we go. And so I was pulling from list 1 and list 3, but I just put my data in list 1 and list 2. So I'm going to go down here and I need to change this. And to change this, I want to go to list on my calculator, which is second stat. And I'm going to tell it to pull my Y data from list 2. And so now this changed from list 1 and list 2. Okay? So I go back out of here. I'm all done. So I can quit out. So second mode, quit out. And now I want to look and see if I can see the data. So I'm going to hit graph. And I can see that my axis is all wonky, so nothing shows up. So I'm going to do zoom, and then I'm going to do zoom stat, which is option 9. And now I can see my data. Okay. Now, the other thing that we want to do is you need to make sure, and I have this on the notes here, that you need to make sure that your stat diagnostics is on. And so if you go into the mode button on your calculator, you want to go all the way down to the bottom and you want to see stat diagnostics on and stat wizard. So if you have an older calculator, you might not have this option for stat wizard, but make sure that your stat diagnostics is on, because we're going to need that when we run a best fit line. Okay, so if I look at this data, if I wanted to describe this data, so I'm going to go in here. It doesn't ask us to do it, but it's a good process here. So remember, Duff's is what I'm looking for. So my direction on this is positive. So I know that this is going to be positive. And then a unique feature, this could potentially be an outlier. So I might have one outlier here, and it's easy to see where that data point is. So that data point that's going to happen is going to be this one at 6 and 60. So this might be an outlier. My form, I'm going to say that this is linear. This looks a little bit like it could be exponential, but because I have this potential outlier up here, I'm going to say that this is a linear representation. And then the strength, I'm going to say that my strength of this line is fairly positive. So I would say moderately positive. All right, so this is how this would look. I would say the relationship between number of cigarettes smoked and doctor's visits is moderately positive and linear with a potential outlier at let's see, 60 cigarettes and 6 doctor's visits. Now, we haven't really gotten to association, but I'm going to throw this in here right now because I think it's good to already see this. So what I would say is, and if you look back at your data, you see that as you smoke more cigarettes, your doctor's visits are increasing. So more cigarettes, doctor's visits are increasing. So what I would say is there is an association between number of cigarettes smoked and visits. This key right here, we want to say if there is or is not an association on the scatter plot. The whole purpose of this is to analyze the data and say, okay, is there an association between these two data points? And we're going to get into more of how we're going to know exactly what the association is. But if you just look at the data, the more visits you have, the higher it is. Now, I know you can look at this data and you can see the same thing, but as our data sets get larger, putting on a scatter plot or having a computer-generated scatter plot is going to be a better way to analyze data. Okay? All right, let's keep going. All right, so how do we know if we have a good linear relationship? So that's what this is. In order to strengthen the analysis when comparing two variables, how do we know without just looking at it and saying, okay, we know? Then we attach a number, and that number is called the correlation coefficient, and it has this letter R, and it is used to describe linear association, so only linear graphs. You have to have, you will use this only with linear graphs. And so what happens is this number removes the subjectivity into reading the scatter plot. So a minute ago, when I looked at this, I said, yeah, this is moderately positive in strength, right? But this is going to give us an exact number so we don't have to be subjective, okay? And so what we know is that this correlation measures the strength and direction of the linear relationship. So let me be really clear here. Correlation is what we're measuring. We want to know how close the x value and the y value is, and this is the number part of it. When we describe it, we don't use the word correlation, we use the word association. So we're going to use correlation constant because we're going to have an R value that we're going to give, and it's going to give us a number, but then when we talk about how strong that number is, we use the word association. Okay? So we have this awful formula. I'm going to write it down. We're going to talk about it. I'm showing this to you, but as you see right here, this formula is provided to us on the AP Stats formula sheet, and I'm not really sure when you're ever going to use it because we're going to do everything on the calculator. But here it is. R is our correlation constant. So our correlation constant is R. And we start by having some amount of values minus 1. So we take all of our data points and we subtract this by 1. And what we're doing is we're taking the average of everything minus 1 value point. And we'll get into why that happens here in a little bit. So now we're going to sum up all of our values. And this should look super familiar to you. And this part of our equation is our z-score. So we've found the z-score in relation to our x variable. So each x variable is our xi component. Our mean is our x bar. And our standard deviation is our s sub x. Now we multiply this z-score in the x direction with this part of our equation. And if you look at this, these are our y values. So we have our y sub I, which is each individual value, our mean in the y direction, and our standard deviation in the y direction. So remember, this is bivariate. So we have our x variables and we have our y variables. And the difference is because we have two different axes comparing two different things. So we have height and we have arm length. So we're comparing these two. So we're going to have a deviation, standard deviation, and a mean within height, and a standard deviation and a mean within arm length. And that's why we multiply these two numbers together. Okay? So what it says here, essentially, the correlation coefficient, which is R, finds the average of the product of the standardized scores. Standardized scores being z-scores. So a few little rules or tips about our correlation constant. The correlation constant is always going to be a number that's between -1 and 1. So if we have a value that's -1, we have a perfect negative linear relationship. And so that value on your scatter plot is going to look exactly like this. It's going to be perfectly linear. The flip side is if we have one that is r equals +1, then we have the same thing. We have a perfect linear relationship. And so what we want to see on a scatter plot is we want to see the values as close to -1 or as close to +1 as we can. That's really what we're looking for. That means that we've got perfect data. But if we have something where our correlation coefficient is R, that means there is no pattern. So I could have something that looks like, I don't know, like this. Doesn't go up, doesn't go down. There is no linear relationship. And that would happen when our R value equals 0. All right. So the next little tip or trick or fact that we have here is that our positive correlations between 0 and 1 have varying strengths. So we know that strength is one of the variables that we measure when we talk about describing the characteristic. So strongest positive correlation is 1. So if we have one that's 0.9, that means we're going to have a pretty strong, that's probably too high, correlation. So if I had this and I drew this line, everything fits this line but this 1 point. That is pretty strong. So this would be our strong positive. Now when we look at this on the graph, we would say that this is a strong, S-T-R-O-N-G, strong positive relationship. But this data point of 0.9 tells us exactly how strong it is. So if we have something that's 0.5, then it's probably going to look more like this. If I draw this line that's through here, about half of the data is pretty close to my line. So this would be 0.5 would be something that would be moderately strong. So this would be moderately. That value makes it easy because it's 0.5. if I have something that's 0.2, I'm going to have something that probably looks like this. So I can see that my line is going in this direction. It's going positive. I can see that, but my data is not really hitting anything. So this value here at 0.2 would be a weak relationship. Okay? Now, here's the thing. This is important. So we talk about this being subjective. There's no magic cutoff number for describing weak, moderate, and strong. Okay? So that's why a minute ago when I drew that, I said, you know, I probably would have called that middle one strong instead of moderately, depending on when I drew this. So even with these numbers, we know that a high number is going to be strong. We know that a mid number is going to be moderate. We know a low number is going to be weak. All right? So we have the same thing with negative correlations. Save time, I'm not going to graph these, but we see it's the same thing. This negative 0.9 is going to be an almost perfect negative line. So I said I wasn't going to draw these, and now I am. So I would have something that looks like this. And so as I draw this line, I see I hit all the points, but maybe this one point right here. Okay? All right, a few other little tips here. Switching the explanatory and response variables on the axes will not change the correlation. So if I would have changed this and made this arm length and made this height, the slope of my line is not going to change. I'm sorry, let me restate that. The slope of my line is going to change because my arm and my height, but the correlation is not going to change. So correlation makes no distinction between these two variables. So it doesn't matter what x is and what y is. It's going to give you the same r value if your variables were this way or if your variables were this way. Same r value gets popped out of both of those. Okay, next little tip here. All right, so if we look at this, a lot of people would say, okay, this is a correlation constant of -1 because it is a perfect quadratic relationship, but this is not the case. And the relationship here is, or the reason is because correlation only describes linear relationships. So because this is going up and this is going down, we would say that we would have a correlation of 0. There is no linear pattern here. So the correlation here would be 0. We would say that it is, there's no relationship. Okay, the correlation constant, the R value, is very strongly affected by outliers. So think about this in terms of a distribution. We know that our mean and our median is affected by outliers. Our correlation is also affected by outliers. So use correlation when with caution when you see outliers in your scatter plot. So don't rely on the correlation alone to determine the length between your two variables. Sometimes it's good to run the correlation and then go back and rerun it again by taking out that variable. All right, so no units with correlation. So unlike standard deviation where the units match whatever we're measuring, there are no units with correlation. We're just going to get an R value. R equals 0.3. And then this correlation doesn't imply causation. So causation, this word causation, is the same thing that we say when we say association. Does one variable cause the results of another variable? Is there an association between our two variables? So is there, if I go back to my very first graph right here, we would say that there is an association between arm span and height. The longer your arm span, the taller you are. There is an association here. We would say that there is causation. Now, when we describe it, we use the word association, but to determine if there's this association, we have this causation. So here's an example of this. Does an increase in skiing revenue, so our revenue is increasing, cause more people to die by being tangled in their sheets? So I pulled this graph from your textbook, and this is, I would say, an almost perfectly linear relationship. So this would be, describing this would be very strong, positive, linear relationship. Okay, very strong, positive, linear relationship. However, let's think about this causation. If you have more revenue from skiing, are you more likely to die by being tangled in your bed sheets? No, that's ridiculous. That doesn't make any sense. So you have to look at the data and make sure that the data makes sense. Like, this is an extreme situation, but think about two things. Can you really die from being tangled in your sheets, and it's going to increase your skiing revenue? So that's what this means. Just because this shows correlation does not mean that there's causation. All right. If asked to draw scatter plot, so now we are not asked to draw a scatter plot on the AP Stats test, but don't just copy your screen. Make sure that you have labels on your axes, and it's not going to ask you to do that anymore. Okay, so here's a couple practice problems. So with this problem on the left, it says that the left shows the relationship between the duration, so the time in minutes of an eruption, and the wait time until the next eruption in minutes of Old Faithful Geyser in Yellowstone. Describe this relationship. Okay, so if I look at this, the first thing that I see is that there's definitely a positive relationship. So if I draw this line that's through here, I would have a strong, linear, positive relationship between let's see, I want to say geyser eruption and duration between eruptions. Oh, it's not geyser eruption, geyser wait time. So geyser wait time and duration between eruptions. There we go. ERUPTIONS. Okay. So I also see that I have two clusters here. So we have two clusters. One at about 2 minutes. And another at, I'm going to say 4.5 minutes. All right. I don't know if I have any outliers on here, so I might say that this is a potential outlier, but I don't think so. I'm just going to say there are no obvious unique outliers or leverage points when we get to that. All right, so let's make sure we have everything. So DUFS, direction, so positive. Unique features, I talk about clusters and I say no obvious outliers. My form, I said linear, and the strength is strong. So I've got all of my parts there. Okay. If we look at this next one, it says the scatter plot on the right shows the relationship between the average income in dollars and the fertility rate, so the number of children per woman in 187 countries. Okay, so what I see right here is a relationship that looks like this. And so that would absolutely be nonlinear, right? I can't really draw a line. I've got too much data that's in here because the slope of this line would just be too steep to hit enough points. So, but this looks, I mean, I can look at that and see that it's an exponential decay function. So I'm going to say this is still strong. So I have a strong, you know what? I've got a few up here. I'm going to say moderately. I'm going to say moderately strong, negative, non-linear relationship between fertility rate and average income. So this could be an influential point. These could be influential points. Now, these might not be outliers. These might not be influential points out here. And the reason for this is because it follows this curve. Now, there is a big gap that happens right here. And so because we have this gap, we might have these leverage points that are out here, but we don't know that yet, right? So when describing, I'm just going to describe this, and I could say there is a potential outlier at, let's see, I'm going to guesstimate this. I'm going to say approximately 38,000 and 4.7 children. So here's what I have. Moderately strong, negative, nonlinear relationship between fertility rate and average income. Potential outlier at approximately 38,000 and 4.7 children. And leverage points, possibly above 120K. Now, I don't know anything about this, so remember I have to use that vague terminology in here. So potential outliers, possibly these 2 points could be outliers, but I don't know exactly. All right, so let's look at this. So direction, I have my direction. My direction is negative. Unusual outliers, I say right here we have a potential outlier. My form, which is nonlinear, and my strength, which is moderately strong. Okay, now because we don't have all of these data points, I can't run the calculator to get my correlation constant. I can't do that yet. Okay, all right, last thing down here. Interpret a scatter plot showing the relationship between height and free throw percentage for a random sample of 20 WNMA. I think this should be NBA players. Yeah, free throw, NBA, WNBA. If this was R equals negative 0.4027. So what would we say about this? So if I'm interpreting the scatter plot and this is all I have, what I would say is that a correlation constant R of negative 0.427 indicates a negative actually, hold on. I would say before negative, I would probably say a moderately strong, negative, linear relationship between height and free throw percent. All right, let's talk about what's important here. So this is negative. I talk about negative 0.427. That's moderately strong. That's right about in the middle. Remember, we want our values to go from 0 to -1. So if I have 0.427, that's about in the middle. Now, here is the key, linear relationship. So we know that this is linear because only linear relationships can give us an R constant. If it hadn't given us this R, I forgot my T on constant. If it hadn't given us this R value, then we don't know if it's linear or not. So we have to imply here that we understand that this R correlation constant tells us we have a linear relationship. Okay? All right. In the next lesson, we'll learn how to actually calculate this value on your calculator. Okay?